So we reached chapter 5 and we are in polynomials. The name of this chapter is called polynomials. So here in section 5.2, we're going to finally figure out what polynomials are. Before we get started, quickly, your assignment will be pages 231 to 232, numbers 17 to 53 odd, 63 through 65 all. Let's take a look at our vocabulary. So poly means many, and nomial means number, and so polynomial means many numbers. Remember monomial from the last section? Monomial was one term, right? It was like if you had a term like 3x squared or 2xy or 7. These were all monomials. Well, if I string them together with addition and subtraction signs, then it becomes a polynomial, right? And it's a polynomial particularly if you can't simplify it any further and you've got these different sections that are being added together, different monomials that are being added and subtracted together. So poly means many nomials, many monomials in a sense, being added and subtracted together. So 7 minus r, 3 over 2 x squared minus y plus z. All of these are considered polynomials. Terms. Now terms are each part of a polynomial. So here's a polynomial term. 3x squared is the x squared term. We've got 2xy, that's the xy term, and the constant term is -7. So terms, in a sense, are the parts of a polynomial. Like terms are just what you think they are. They're terms that are alike. So if I had a polynomial that was like 2x squared plus x minus y minus 3x squared, here this polynomial has like terms, and those like terms I have highlighted here in red would be this x squared term and this x squared term, and I can bring those guys together to simplify this polynomial, so that instead of having 2x squared plus x minus y, I actually have negative x squared plus x minus y, because these guys came together, added them together, and I got a negative 1x squared or negative x squared. And I cannot simplify any further, so this is the simplest way that I could write this polynomial. Now, polynomials have specific names depending on the number of terms in them. This polynomial right here, I'm going to grab it and slide it down over here. This is a trinomial. Want to take a guess why? I think you see it. I'll wait. Waiting for you to say it. Yeah, that's exactly it. It has three terms. Three terms that don't simplify, that aren't like terms. So it is a trinomial. Want to guess which one up here is a binomial? I think you see it. Two terms, can't resolve. It's a binomial, two terms. So binomials will look like x plus 3. Technically, actually, x squared plus 2 is a binomial because it only has two terms. Generally, we're going to see binomials of the form x plus 3, x minus 9, so forth and so on. Trinomials have three terms. And FOIL. When we get to the point where we are multiplying binomials, so I might try to multiply x plus 3 times, let's say, x minus 9. What I'm going to have to do is something called a FOIL method. And basically, it's a method to make sure you multiply each term of this binomial with this binomial. So in my mind, I think, okay, I'm going to take this x and I'm going to multiply it with this x, and I'm going to take the same x and multiply it with the 9. After I do that, I'm going to take the 3 and multiply it with this x, and then I'm going to finally take this 3 and multiply it with this 9. Well, each of these colors, if I think about what happened, I multiplied the first two. That's F. Then I multiplied the outer two. That's O. I think you guys see where this is coming. Then I multiplied the inner two. That's I. Then I multiply the last two. That's L, last two. And what does it spell? F-O-I-L, FOIL. And that's the FOIL method. I'm actually, for years I taught the FOIL method. I kind of like the idea of actually thinking about this as simply the extended distributive property, because to me it makes more sense. And I just like to tell students, hey, take the first term, multiply it with each of the terms in each of the other two terms, and then take the second term and multiply it with each of the two terms, instead of remembering F-O-I-L. Not like that's a hard thing to remember, but just saying. So sometimes you'll hear me refer to the extended distributive property. I'm going to extend the distributive property where I'm distributing everything in this parentheses into the other one, all right? So With that, let's go ahead and take a look and talk about what we have here in terms of example number one. It says determine whether each expression is a polynomial. If it is a polynomial, state the degree of the polynomial. Okay, so remember a polynomial is a bunch of or a few or two or more monomials being added or subtracted together. This is a monomial, this is a monomial, and I'm going with yeah, you, my friend, are a polynomial. So I'm going to write yes, polynomial. Got a polynomial here. Yes, this is a polynomial. And what is the, if it is a polynomial, state the degree of the polynomial. Now, the degree of the polynomial, you remember we talked about degree in the last section, degree of the monomial. We add up all of the number of variables that are being used in whatever term. So the degree of this monomial right here, if I just look at this one, is 8. And the degree of this one is 4. So the degree of the polynomial, the polynomial always takes the degree of the largest monomial. So the degree of this polynomial is 8. So I'll just write degree 8. And let's come down here and take a look at this one. Is this a polynomial? And the answer is actually no. Can you guess why? Well, if you can't, it's really just because of the definition of a monomial. The definition of a monomial says that it's a term, it's a collection of x's and y's and variables, but that where the exponent is always a whole number, right? And so this exponent is 1. The exponent here, which we're going to learn, is actually 1/2. So we can't have a monomial with radicals or fractional exponents. So since that is not a monomial, this thing is not a polynomial. Weird, right? So no, not a polynomial. And so because it's not a polynomial, we're not going to go to the follow-up question, who is whether it's what is the degree of the polynomial, because it's not a polynomial. All right, addition and subtraction and simplifying. To simplify these guys, when we're subtracting two polynomials, in this case they're trinomials, if I'm subtracting, I'm going to distribute that negative through. So I could rewrite this. The first trinomial stays the same, and then the second, I'm subtracting everything. So in a sense, everything kind of multiplying through by a -1, everything inside changes its sign. -1 times that's going to give me a -x squared. -1 times that's going to give me a -4x. -1 times that is going to give me a +2. Now what I'll do is I will identify like terms. So this is like this. This guy is like this guy. And finally, this is like this. I can barely see that. These are my constant terms. And so what I'm going to do is I'm going to join those like terms together. This is what it means to subtract and simplify. Not too bad, right? I feel like we've done this before. 3x squared minus x squared is going to leave me with 2x squared. So I've taken care of those guys. Minus 2x and a minus 4x gives me a minus 6x. Taking care of those guys. And finally, this 3 and this 2 come together to give me 5. So I have done the thing. I've subtracted these two polynomials, which both happen to be trinomials, and my result was a trinomial, and I'm done. Example 3, we're going to multiply. This kind of multiplication is straight up ordinary distributive property. So the thing on the outside, I'm going to multiply throughout everything on the inside. So I'm multiplying this term by all of the terms in this polynomial. So 2x times 7x squared is going to give me 14x to the third power. Remember, multiplying two numbers with the same bases pumps up the power of that particular base, so it goes x to the third power. 2x times a -3x is going to give me a -6x squared. And then 2x times a +5 is going to give me a +10x. And I'm done. There's no simplification because there are no like terms. There's nothing I could join together. So I've done what I needed to do. Let's go on to example 4. Over here in example 4, now we're multiplying two binomials, and this is where we would use that vocabulary word that, I mean, lots of teachers talk about it, doing the FOIL method, and really it makes sense. I just always hate memorizing what the FOIL method means. So what it does mean, if you like this method, I'm going to share it with you and tell you that you multiply the first two, that's your F, then you do the outer two, and that would be your O, so that's the outside two, like these two numbers are on the outside. And then you would do the inner two. Let's do the inner two. Let's use purple, I guess, for that. Inner two, and let's do blue for the last two. And so that's where you get your FOIL. Like I said before, I don't do that. I mean, I do it ultimately, but I don't usually do it. I don't usually say it that way. Just call it the extended distributive property. I'm going to take this guy, multiply him with him and him. And so I'll do that now. 3y times 5y is 15y to the second power. That's 2 y's there. 3y times 4 is going to be plus 12y. Now I'm going to go ahead and multiply this guy times this guy and this guy times this guy. So 2 times 5 gives me a 10y. And then 2 times 4 gives me a plus 8. And so now I'm going to join these like terms together. These y terms are the same. And when I do that, let's write it in black. 15y squared plus 22y plus 8 is my answer there. Not too bad, huh? All right. We have a couple more examples to go. Here we have multiplying polynomials. So now the FOIL method fails here. This is why I kind of don't love it, because the FOIL method only works when you multiply two binomials together, but the extended distributive property, now that works all the time. I'm going to take this term, I'm going to multiply it with both of these terms. I'm going to take this term, multiply it with both of these terms. Take this term, multiply it with both of these terms. Get all of these new terms, these products, and I'm going to add them together. So let's go get started. N squared times this guy, n squared times this guy. It's going to give me n to the third power plus 4n squared. That's me multiplying these two. Next, I'm going to do 6n times n and 6n times 4. And when I do that, I get a plus 6n squared and a plus 24n. The next thing I'll do, and the final thing I'll do, is this last one, negative 2 times this term and negative 2 times that term. Negative 2 times n gives me a negative 2n, and a negative 2 times 4 gives me a negative 8. Now it's time for me to collect my marbles and join my like terms together. So n to the third power is all by herself, but n squared has a couple of terms. There's a 4n squared and a 6n squared. This n, this single n, or n to the first power, has a couple of buddies, 24n and a negative 2n, and this constant term is alone. So let's go ahead and get it together. I'm left with n to the third power. That was alone. Join these guys together. I get plus 10n squared, and bring these two guys together. I get a positive 22n and a negative 8. Notice none of the terms that are left have anything in common, and so I'm done. I'm done with that one.
Whoa, look at this.
Let's take a look at this next example. Oh, we don't have any. Aren't you happy? So we're done. The examples that we're going to talk about today, which is kind of cool. So basically your assignment is really going to be to practice these concepts, right? You're just going to be practicing these concepts, and you want to get good at it. So I know it looks like I gave you a lot. It's not that many when you see it. Please make sure you give it a try and let me know if I can help you in any way. Take it easy.